At the end of our last lesson, we discussed the division theorem, but we did not prove the statement. So the plan for today is to prove the division theorem. We're going to need some lemmas before we get there. And afterwards, we're going to transition over to chapter 4 of our textbook, starting section 4.1, Cartesian products and ordered pairs, which will allow us to discuss in the language of set theory the notation that we saw in calculus and linear algebra, namely R2 or R3 or Rn. How do we describe these spaces in terms of sets? And so that's going to be the motivation for section 4.1. So to prove the division theorem, we first need the following lemma, which is also referred to in some number theory texts as the zero theorem. And so what it says is, let a and b be integers, then a times b is equal to 0 if and only if a is equal to 0 or b is equal to 0. And this is something that we have used throughout our solutions to equations. Whenever we have a product that is equal to 0, we know one or the other is equal to 0. So let's prove this. And I'll make a note that we're going to prove this, but technically it's going to rely on a fact that we are not going to prove, but we'll prove later in the course when we actually discuss what are the axioms of the integers. And so for now, this is sort of a proof with a assumption that we'll prove later. So here's the proof. So I'm going to do one direction first, so the reverse direction. So let's do the reverse. So suppose a is equal to b is 0 or b is equal to 0. Now, the section that we discussed last week, whenever we have a proof where the assumptions are a disjunction, we have to do one case. So assume that a is equal to 0, and then we'll have to do the other case, that b is equal to 0. But the symmetry of the argument here is going to be exactly the same statement if we did it for a is equal to 0 or b is equal to 0. So in instances like these, there is a phrase that we use, and it is called without loss of generality. So without loss of generality. And so we can go ahead and abbreviate it as WLG. Suppose that a is equal to 0. And the idea here is, by using this phrase, we are informing the reader that both situations that we have to assume are essentially identical. And so we are only going to do one case, namely a is equal to 0. And so suppose a is equal to 0, then a times b is equal to 0 times b, which is equal to 0, which concludes this case. And so now we have shown that one direction. And the disjunction, we didn't have to do it in the sense of how we did it last week of doing one case and then the other, since we used the phrase without loss of generality. So let's do now the forward direction. So now we have to assume that a times b is 0. And so we are going to go about this via contradiction. So towards a contradiction, suppose that, and so now we're looking at the negation of this statement, and so that will become a is not equal to 0 and b is not equal to 0. And so we have that both a and b are not equal to 0. Now, if a and b are both not equal to 0, then we have the possibility that a and b are both greater than 0, that a and b are both less than 0, or they have different signs. And so here's where we are going to use the fact that I mentioned earlier. So specifically, we're going to be using the following fact. If a and b are integers, then a times b is positive, if and only if both a and b are positive, or both a and b are negative. We have discussed the Zermelo-Franco axioms in previous lessons. And so these are the axioms upon which modern mathematics is built upon. And then from it, one can deduce what are the properties of the integers. And oftentimes the minimal properties that one gets from the Zermelo-Franco axioms for the integers are taken in number theory texts to be the axioms of the integers, which we will be discussing later in the course. And as an illustration of how one proves statements directly from the axioms of the integers, we are going to come back to prove this statement. And so for now, we're taking this as a fact, but we will come back to this later in the course and prove this from the axioms that we will discuss for the integers. But again, when I say axioms, these are proven via the Zermelo-Franco axioms, to be precise. Okay, so here's how the proof goes, if we assume the fact. So now, we know that both A and B are non-zero. So if A and B are both positive, or A and B are both negative, then the fact below implies that the product of A times B is positive. So that means that both A and B have different signs. Consequently, we have that one of A or B is positive and the other is negative. So I'm going to go ahead and do this by cases and then discuss a way that we can simplify the argument in our writing. And so we have a disjunction here. A is positive or B is negative. Sorry, A is positive and B is negative, or A is negative and B is positive. And so we have two cases to consider because of that disjunction. So suppose A is positive and B is negative. Well then, we have that negative B, which becomes now positive, times A is a positive quantity. By the fact that we have down here. Since now we have that both A and negative B have the same sign, they're both positive quantities, so now this is greater than 0 by the fact. And so A times B is not equal to 0. And then same situation here, the same exact argument will hold, except now we have, suppose A is negative and B is positive. And then we do negative A times B is positive by the fact until AB is not equal to 0. Hence, and so this concludes the proof. And we're done. And so we can end the proof here. Now, something that we could have done to simplify this, because these two arguments are exactly the same. So what we could do is do the following phrasing to replace case 1 and case 2. And what we are going to do is inform the reader that we can interchange A and B respectively. And so we could say the following phrase right after is negative. So after interchanging A and B, if necessary, we may assume that A is positive and B is negative. And then we can then do the same exact argument that we did. So negative b times a is positive by the fact, and thus ab is not equal to 0. And that finishes off the proof. And so when we use this phrase, what we are saying is that if we were in case 2, we just interchange the a's and the b's. So that now, in this situation, b was positive, but we are interchanging it so that now a becomes positive. And similarly, a was negative, but now that becomes b, and so now b is negative. And so we are only considering case 1 by doing that interchange. So let us revisit our definition of what it means to be a factor. So we said that given an integer a, an integer d is said to be a factor of a if there is some integer k such that a is equal to d times k. Well, we can also say instead of factor, divides. And so we can say that d divides a if there is some integer k such that a is equal to d times k. And so divides and factors are both equivalent notions. Now, with the divides, we use the following symbol to denote this. And so then whenever we say this, we mean d divides a. And so the first statement we are going to prove is that if a and d are positive integers, if d divides a, then 1 is less than or equal to d, less than or equal to a. So here's the proof. So suppose that d divides a. Then there is an integer k such that a is equal to d times k. Now, let's make the following observation. Since a and d are positive integers, we note that k is a positive integer. Now, since k is positive, we have that 1 is less than or equal to k. And now what we are going to do is multiply both sides of the inequality by d. So we have d times 1 less than or equal to k times d, which by definition is what we define to be a. Hence, d is less than or equal to a. And so we are done. And now here's where we use, when we talk about the axioms the minimal axioms for the integers, what we are going to see is that one of the axioms that we will have is the notion of the one that pertains to inequalities. And so what we are using here is that since we have this inequality here, and d is a positive integer, then we end up getting this we can multiply both sides and preserve the inequality here. And so we'll come back to this towards the end of the course when we formally discuss the axioms that build the integers. So now we can prove the division theorem. And so I've changed it slightly from how it was phrased in the last video. So now I have a as a natural number and b as a positive integer. Now, by allowing a to be a natural number, we now have to consider the case when a is equal to 0. And so what we are going to do for the proof is consider the case when a is 0, separate from the case when a is a positive integer. So proof, let's go about the proof now. So first suppose that a is equal to 0. Then, for each positive integer b, it is the case that 0 is equal to b times q plus r, where q is equal to r, which is equal to 0. And so we have shown the existence. So now suppose that a is greater than 0. So now, suppose that a is a positive integer. And we're going to proceed by induction. And so what we are going to do is make an induction argument on a. And so let S of a be the statement and so now we go ahead, we write the phrase up here. So for each positive integer b, there are integers, and so we're doing with induction the existence portion, and so there are integers b and q, q and r, such that a is equal to b times q plus r. And so the key thing is our integer a is fixed, and so the statement depends on a. And so we're fixing the integer a, and we're saying that for that given a and any positive integer b, then we can find integers q and r such that a is equal to b times q plus r. And so now we proceed by induction on a. Now for the base case, I'm going to put in some scratch work, and I'm just going to put this in brackets and in blue. So this is going to be separate from the proof, just to get us to see what we need to be careful with. So here we now assume a is equal to 1. So then we're going to have 1 equals b times q plus r. But b is an arbitrary positive integer. And so we need to be careful, because if, say, b was equal to say 5, then we can easily take q to be 0 and r to be 1. But that only works if b is not equal to 1. And so we have to consider two cases. If b is equal to 1, then we can take q to be 1 and r to be 0. If b was greater than 1, then we can take q to be 0 and r to be exactly equal to 1. And in both of these cases, we have that r is strictly less than b and r is strictly less than b. Since now we have 0 is less than our b, which in this case happens to be 1. And down here, b is greater than 1. And now our r is 1. And so that's the idea behind the base case. So we do have to break it into these. We have to consider these two possibilities. Since now b is allowed in the statement to be some arbitrary positive integer. So now let's go ahead, let's return to the formal write-up. So suppose a is equal to 1. If b is equal to 1, then we have that 1 is equal to b times q, which I'm going to write just as 1 times q plus r, where q is equal to 1 and r is equal to 0. So that takes care of that case. And so now if b is greater than 1, then 1 is equal to, now we're going to write b times q plus r, where now we take q to be 0 and r to be equal to 1. And so we're done. So this establishes that S of 1 holds. So S of 1 is true, and thus the base case holds. So now we need to move on to the inductive step. So now suppose that S of A is true for some positive integer A. Okay, so if S of A is true, that means that for any positive integer B, it is the case that there are integers Q and R such that A is equal to B times Q plus R. So let us go ahead and write that down. So in particular, for each positive integer B, there are integers Q and R such that A is equal to B times Q plus R, and 0 is less than or equal to R, which is strictly less than B. So now we want to show that S of A plus 1 is true. So now consider A plus 1, which is equal to B times Q plus R plus 1. And we have a bunch of symbols now, but what we want to do is find new integers Q prime and R prime, say, so that we could say that this here A plus 1 is equal to B times some Q prime plus an R prime. And now let's revisit our motivating example from the end of our last lesson. If we started off with A was 58, B was equal to 3, then to get to A plus 1, that is 59, we add 1 to both sides as we just did, and what we end up getting is 3 times 19 plus 2. And so now we can take 2 to be our remainder, and our Q remains the same. But we have to be careful, because if we had then started with 59 instead, added 1 to both sides, we would have gotten 60. And then now the remainder would be 3, but because our B is 3, that is not in fact the remainder, and so then we have to factor out. And so we're going to break this into two cases. So we consider the following two cases. And so now we now consider the cases when R plus 1 is less than B and R plus 1 is equal to B separately. So case 1, suppose that R plus 1 is less than B. Then let Q prime be equal to Q and R prime equal to R plus 1. So that we then have that A is equal to B times Q prime plus R prime with R prime less than B by construction. And so we have essentially now gotten our existence in this situation, and we are done for that case. Case 2. So now here, we're going to suppose that r plus 1 is equal to b. So let q prime, and here's where we go back to our motivating example. What we want to do is take our q prime to just be q plus 1. And so we take our q prime to be q plus 1. And r prime to be equal to 0. Then a, which is now equal to b times q plus r plus 1. And now r plus 1 is equal to b, so this becomes bq plus b, which is equal to b times q plus 1 upon factoring out the b, which is the same as b times q prime plus r prime. And so we are done with this case. So in particular, S of a plus 1 is true, and so by the principle of mathematical induction, we conclude that S of a is true for each positive integer a, which shows the existence portion of the theorem. And so now we have shown the existence of the q and r for every positive integer a, and since we did the case when a was equal to 0 separately, we have now shown the division theorem, at least the existence portion, and all that remains is to show uniqueness. And so it remains for us to show uniqueness. And so to this end, let us go ahead and suppose we have a is a natural number, b is some positive integer, and now we are going to take a q prime, r, and r prime to be integers, and then we want the r and r prime to satisfy the following inequality, where we have 0 is less than or equal to r and r prime, and both are strictly less than b, such that we have the two equations, a is equal to bq plus r, and a is equal to b times q prime plus r prime. And what we want to show is the uniqueness portion. So we want to show that both q is equal to q prime and r is equal to r prime. And so what we are going to do is subtract the two equations. So if we subtract the two equations, so subtracting the two equations yields that we have a minus a, so 0, is equal to bq plus r minus bq prime minus r prime, which is equal to bq, and then we have minus q prime plus r minus r prime. But now this equation implies that we have b times q minus q prime is equal to r prime minus r. For uniqueness, we need to show that r prime is equal to r, and so in other words, r prime minus r is equal to 0. So we claim that r prime minus r is equal to 0. And so now we're going to do a contradiction argument to show that it must be 0. So for a contradiction, suppose that r prime minus r does not equal 0. Now, this gives us two possibilities. R prime minus r is going to be positive, or r prime minus r is going to be negative. So after a possible interchange of r and r prime, we may assume that r prime minus r is greater than 0. And now we use the lemma. Then by lemma 2, we have that b divides r prime minus r implies that b is less than or equal to r prime minus r. And so notice that we are using now the assumptions. Because for lemma 2, what we had is that a and d are positive integers, and our a is r prime minus r. So interchanging r and r prime if necessary is crucial so that we can assume that r prime minus r is positive, and now the lemma applies. And so we have that since b divides r prime minus r, it is the case that b is less than or equal to r prime minus r. And that's where we are right now. So we have b is less than or equal to r prime minus r. But now let us return to our assumption on r prime. So we have r prime is less than b. So here we're using our assumption. And so if we go ahead and subtract a r from r prime, we have that this is going to be strictly less than b minus r. And now b minus r is going to be less than or equal to b, since r is going to be between 0 and b. And so we have this inequality. So thus, we have b is less than or equal to r prime minus r, which is simultaneously less than b. But now this is a contradiction. Indeed, we have essentially shown now that b is strictly less than b. And so we are done with this, so now hence r prime is equal to r, which establishes uniqueness. Of r. So where do we go from here? So let us come back. So now we have established that r prime is equal to r. So now this is equal to 0. So therefore, we now have that b times q minus q prime is equal to 0, which by lemma 1, we conclude that q minus q prime is equal to 0. And so as a reminder, lemma 1 is the zero theorem. And so the zero theorem tells us that if a times b is equal to 0, then that's equivalent to a is equal to 0 or b is equal to 0. But in our case, we know that b is a positive integer, so it is non-zero. And so since b is non-zero, it must be the case that q minus q prime is equal to 0. And so we conclude q minus q prime is equal to 0 since b is non-zero. Thus, q is equal to q prime, which concludes the proof. So now that finishes it off for the division theorem. But now, this proof is by far the most complicated argument that we have done in this course up to this point. It is an existence and uniqueness proof, but to show the existence we used induction in a way that was different than the material that we covered in 6.1. And the main takeaway from this is how versatile induction can be. It goes beyond just proving formulas of how one can add up integers or multiply them, as were the homework exercise in 6.1 conveyed. But we could do it in this manner, where for the division theorem, we constructed this statement S of A, and by proving that statement, we were able to establish the existence portion. But the proof was heavy on symbol manipulation. And behind the scenes was our example that was used as a guide. And so it's important to keep this in mind as you read through proofs in the future, as well as craft your own proofs. Sometimes it is good to do a numerical investigation to see what is happening. What will happen as we go to the induction step in a concrete case? Because in the proof itself, that aspect is not clear. There are two cases that we considered as part of our inductive step, but those two cases were motivated by the example that we did at the end of our last lesson. And so please keep this in mind as you craft your own proofs as well as read proofs in the future. Is if we want to get a handle for what is going on behind the symbols, just plug in concrete values and use that example to build your intuition for what is going on. So now we're going to move on towards chapter 4.1 of our textbook, so ordered pairs and Cartesian products. But before we get started, I want to motivate this, as you have already seen these concepts before. So let's take R2. Another notation for this is R cross R. And so that's how we discussed this back in calculus or linear algebra. But we can also, as we will see today, this is the Cartesian product of R with itself. And so what we want to do now is investigate what is this as a set. So one aspect is quite easy. So this is just what we defined back in calculus and linear algebra. It's just a set of tuples, x comma y, such that x comma y are both real numbers. Okay, but now this begs the question. Then what is x comma y? We have come to interpret this as the points on the plane. But now we want to describe everything in the language of sets. And so one candidate would be, we could take the set of x's and y's to be equal to x and y. And this is, by the way, this is not correct. This is just to motivate where the definition is going. So this is one possible candidate. But the problem is that then this here is the same as y comma x. And so if we took this to be a definition, we are in trouble, because now we have that this is the same as y comma x. And so this is not a good candidate. And so we want to have a definition that is able to tell us the order of this. And so this is what we are going to be calling an ordered pair. And so the definition that we are actually going to be taking is the following. And so let's go ahead and define an ordered pair as a set. And so now let us go ahead and say that A and B are sets. So let A and B be sets. So now let X be an A and Y be in B. The ordered pair x comma y is equal to the set containing x and the set containing x comma y. And so that's our definition for what it means to be an ordered pair. And from it, we build the definition for a Cartesian product. And so now next definition. So let A and B be sets. The Cartesian product of A and B denoted A cross B is the set. So now we can go ahead and use the definition, since now we have defined what it means to be an ordered pair, the set of x of tuples x comma y, such that x is in A and y is in B. So in other words, this here is the set of sets x comma y, close, and x is in A and y is in B. And so this is the main aspect, is that while we are going to be using the notation for ordered pairs, this is nice and succinct. This really is a set of sets. And so the set containing the x comma y. And so those are the actual elements of the Cartesian product. And so the idea with the Cartesian product is that we can now take Cartesian products of any two sets. So we had the set A, cat, comma, dog, and B, the set 1, 2, 3. Then the Cartesian product is going to be the set of ordered pairs, where now we have cat, so cat, comma, 1, and then we're going to have cat, comma, 2, cat, comma, 3, and then we do the same thing, where now we have dog, comma, 1, dog, comma, 2, and lastly, dog, comma, 3. And so we've exhausted all the possible candidates that we can have in terms of ordered pairs. And so we have this set of 6 elements composing the Cartesian product of A cross B. Let us do the following lemma using the definition of what it means to be an ordered pair. So if A, so let A be a set, if x comma y are in A, then the ordered pair x comma y is in the power set of the power set of A. So prove, let x comma y be in A. By definition, we have that x comma y is equal to the set of pair tuple x comma x comma y. And so we have this here, and we want to show that this is an element of the power set of A. But now, what we do have is that x is a subset of A, and the set containing x comma y is a subset of A. And so since x and x comma y are both subsets of A, we have that x and x comma y are elements of the power set of A. But now if we take the set of these elements, so therefore, if now we take the set of the set containing x and the set containing x comma y, since these are elements of the power set of A, we now have that these are subsets of the power set of A. And thus, x comma y, since this here is equal to x comma y, is an element of the power set of A. And so we are done. So next we are going to consider the following theorem. And so this tells us the properties of how the Cartesian product relates with intersection and unions of sets. So if we have A, B, C, and D are sets, the first statement tells us that if we take the Cartesian product of A with an intersection of B intersects C, that is the same as A cross B intersect the Cartesian product of A and C. Similarly, we have the statements from 2 through 5. And what I am going to do is not prove each of these statements, since statements 1, 4, and 5, these are in the textbook. And so I want us to consider the case of 2 and 3. Before we get into the argument itself, I'm going to do a demonstration similar to how we had Venn diagrams that will allow us to visualize what is going on. And so what we are going to do is assume that we had that A and C, so here I'm drawing something that looks akin to the plane that we are used to. So let's say that this here is our set A. And over here, let's say that we have our set C. And so C is in red. Then our set B, let's say it's over here. And let's take our set D, so here's some overlap, to be this. So now, if we're looking at A cross B, so A cross B is going to be everything above A and everything to the right of B. And so the overlap of the two. And so what we're going to be looking at is this region right here. And so that right there is going to be A cross B. And the whole region, if we go all the way around, all the way to C, and so now that whole region would be A union C, Cartesian product B union D. And so we will be looking at the whole rectangle for that. Now, if we were to look at, say, part A, we have Cartesian product of A with B union C, and so this picture does not apply. We will have to rearrange it. But just throwing this out there that we could use these visualizations to get that. So if we wanted to do a visualization for 2, and so for 2, we would have A Cartesian product with B union C. Here's our B union C. And so what that would look like is this corresponding rectangle. And so that's the whole region. But now if we instead had done A Cartesian product with B, then that would give us the following. So then we have A and B. And so that will be, actually let me do that in red. So this right here will correspond to A Cartesian product B. But then for A Cartesian product C, we would have, and then this portion over here, and then going up, we will have A Cartesian product C. And so the main thing is that now we have A Cartesian product C is this here, and A Cartesian product with B is going to correspond to this here coming down from the red. And so there's that overlap. So when we take the union, we see that we do in fact get the larger rectangle. And so we expect these here to of course be equal. Now to sketch the argument for the proof, we can have, so we're going to choose an x comma y, and so this is for 2. So we choose an x comma y in B union C. By definition, this is going to be x in A and y in the union of B and C. And so now that's by definition. If we apply the definition of the union, this here will be equivalent to x is in A and y is in B, or y is in C. If we apply the distributive law, and so distributive law allows us, we can use this going back and forth. We will have x is in A and y is in B, or x is in A or y is in C. Oops, not or, and. But now if x is in A and y is in B, by definition of ordered pair, we have that x comma y is in the Cartesian product of A and B, or similarly, we have x comma y is in the Cartesian product of A with C. And now that or, by definition of union, tells us that x comma y is in the union of A Cartesian product B and A cross C. And so that gives us the sketch of the proof for this. For the formal write-up of this proof, it is essentially all that we just did, except each step justified. And so in our scratch work, I just said x comma y is in here, and then that is equivalent to this by definition. And so now I've gone ahead, started off with that same statement, and then we have x is in A and y is in the union of B and C by definition of cross or Cartesian product. Then the next line, we can go to it by taking the definition of a union. And so x is in A and y is in B or y is in C by definition of the union. But now if we start here, since everything has been laid out, then we can go back to this stage, since this here is equivalent to this by the definition of the Cartesian product. And so these if and only ifs are justified. And then we go through, we use the distributive law, definition of the Cartesian product, and then finally the definition of a union. And since now we have that this x comma y is in here, if and only if it's in the Cartesian product of A and B, union Cartesian product of A and C, then we do in fact have equality. And so that finishes it off for 2. So now let us move to statement 3. So let's go ahead and visualize this here. So we have the Cartesian product of A and B, and we're intersecting that with the Cartesian product of C and D. So if we take the Cartesian product of both A and B, then that's going to give us this portion right here. So we're going to have this rectangle. And so that's the Cartesian product of A with B. And then if we take the Cartesian product of C with D, that's going to give us the following. And so now we're going to have, here's the C starting over here. And so now this is C cross D. And so what we are looking at for the intersection, it's this common region that they both share in common. And so that's the intersection of the two. And so what this is saying is that if we took the Cartesian product of A and C, and so if we took the intersection of A and C, we're only looking at this portion right there. And similarly, if we took the intersection of B and D, we will only be looking at this portion right here. And the Cartesian product of both of those will in fact be that smaller rectangle. And so we see that the visualization does convey this equality. And so for the scratch work, and I will only be doing the scratch work for this one, what we have is, just as before, we're going to go ahead, take x comma y, but now this is going to be in the Cartesian product of a and b intersect Cartesian product of c and d. And so by definition, that's going to tell us that x comma y is in the Cartesian product of a with b, and x comma y is in the Cartesian product of c and d. So here we're using the definition for intersection. And so the definition of intersection. Then if we apply the definition of what it means to be in a Cartesian product, we have x is in A and y is in B and x is in C and y is in D. But we have and statements, and we know from chapter 1, statements with and are commutative and associative, so we can move things around. And so now what we are going to do is rearrange this so that we have x is in A and x is in C, and similarly we have now y is in B and y is in D. And so now here we're using commutativity and associativity. Of and, since all the statements that we have are with ands. And so now from this we can use the definition of intersection. So this means x is in the intersection of A and C, and y is in the intersection of B with D. And finally, Cartesian product definition tells us that the ordered pair is in the intersection of A and C, Cartesian product intersection of B and D. And so now that will be the definition about the Cartesian product. And so we do have, once again, that the whole process is reversible. And so this will be the scratch work for 3. I leave it to you to formally write this up. And the last thing I want to discuss is part 5 and just emphasize what is going on with this. So when we look at the Cartesian product of A with the empty set, by definition, that is the set of ordered pairs x comma y such that x is in A and y is in the empty set. Now, y in the empty set is problematic because there are no elements in the empty set. And so this here is going to end up being equal to the empty set. But the way to prove that is to go by contradiction. So I'm just sketching the argument. So if we had supposed for a contradiction, that the Cartesian product of A and the empty set was not equal to the empty set, then there exists some x and y in the Cartesian product such that x is in A and y is in the empty set. But the empty set has no elements, so this is a contradiction. Contradiction, since y cannot be in the empty set. And so therefore, it must be the case that the Cartesian product of the two is equal to the empty set. And so that's the idea there, is a consequence of the definition of the ordered pairs that forces the Cartesian product of A with the empty set to always be empty. So this concludes it for today's lesson. Our next lesson will continue talking about Cartesian products, but specifically focusing on relations, which will allow us to define, set theoretically, what a function is.